Hello, good morning. It's Saturday, December 30th, 2023. From a desk of Ross Finlayson, it's me. Here is some more talk about the moment and motion. The idea of an analysis, a dialectic, a consideration as of from nothing at all, how it arrives out in everything, that these are things, the moment, or moments, plural, the singular and the plural, and motion. Is it ever not plural? Motions, motion. So today, what I hope to talk about was, first of all, is that in the earlier talks, largely I always stand by everything I've ever expressly emitted in any of these discussions here that I've recorded in these videos, or, for example, any post I ever wrote to Usenet. I really do. If I find something that I've ever uttered a factual inaccuracy, I care to retract it, to prefer a retraction of this. So the other day, what I said was that the sum of the interior angles of a polygon was 2 pi. And this is factually inaccurate and not true. So I kind of hemmed and hawed, and I qualified it a bit as about the circle. So I said that the sum of the interior angles of a polygon is as of 2 pi about the circle. Because if you consider the interior angles of a circle, what you can kind of consider is that it's infinity. And this gets into one of the reasons why it's difficult to define what is curvature as a property, and that a curvature as a definition of a property has a bunch of different ways that it's identified. So usually curvature as a property is identified with regards to a specific fixed angle and then the interpolation as about it. And so the distance and the radius of how things are drawn for smooth curves as of the Bezier or the French curves or the splines or non-uniform rational B-splines, otherwise matters of interpolation of two straight segments to a curved segment. So anyways, as I was thinking about that, and I was trying to figure out how to address that, because at some point in time I have to say, hey, this was factually inaccurate. But the other day I went to the bookstore, and the proprietor offered me this book, and he said, hey, based on your express interest in what you like, from what I acquire from the bookstore, you might like this book, and I really did. So what this is it's a publication in the education segment. So in the psychology of education, how do people learn? What are ways that it's possible to understand why some people get some things and how they do or don't get the bigger picture or find a faster route. And what it is from a fellow by the name of Max Wertheimer, if I'm not pronouncing it incorrectly. And it's called Productive Thinking. And so this book was published in 1945. And this copy is signed in the frontispiece out of 1948. So what this book is kind of part of the new school after World War II in American education. And what the author really reflects on a lot is the products and the offshoots of what's called the Gestalt setting, which is the combination of things that together make a greater whole, kind of like Kant's sublime, and then this about the phi phenomenon of Wertheimer, which is his great eye-opening with regards to a stroboscope, in effect, what he describes as kind of set him off or made his picture of the continuum or his great stroke of insight, one of these developmental phases in the psychology. That Wertheimer then has as an example this book, and it's geared towards psychologists in learning, and what it's about is why some people grasp notions of the abstract and what can be done to help relay these tactics and skill, because it's learned. just like anything else, the notion of how to develop one's mind is a practice of exercise, and can be very well aided by instruction. At the same time, through various lenses, some things cannot be relayed except as part of a common course and over time. But altogether, the hope is kind of to have an analysis and what goes into helping it so that people can learn, and what the surrounds is from this time and place in the American education system, as what was preferred as basically all the things that became good, and why the 1960s and 70s and the early part of the 80s saw America's great primary science. So, of the new school for social research. It is the first study of the thought processes which develops its conclusions from concrete examples and takes into account the relation of the emotions to thinking, as well as the influence of important human attitudes on the thought process. This volume promises to become a classic in the fields of psychology and education, as well as be a valued generators. So this was a few days ago, and so I'm looking through this book, and he's got a bunch of stuff like, oh, how do you compute the area of a parallelogram, and how about when it's on its side, and he shows different various things that would have been part of elementary geometry and this and that, to get into all these things. And so he's got a variety of chapters in this book, but he got into an example where he was talking to one of his friends about the interior angles of a polygon, and I'm like, oh, I was just kind of thinking about that, and he says that his friend, who was an artist, said it's 2 pi. And so what Wertheimer does is he took that home. He's like, wow, how do I figure this out? How do I break down what he was thinking and how it could be? And so, over time, you think about something like the spiral space filling curve, and its curvature is 1 over r, which makes it a singularity and makes it part of R gauge, which is called the real gauge, big R gauge for gauge theory. And so curvature is a big kind of thing. And like when you think of space-time, the curvature, the idea is singularity, it's infinite there. Or it's 1 over r. So at least in our singularity theory, we have at least 2. One's original and one's the asymptote. But so curvature is well defined. And it's usually defined one or the other of the one-to definition or its inverse. Kind of whatever holds up in terms of whether things are usually turning, and whether a turn is like it's a quarter turn or it's a half turn, or if it's a full turn, all the way around, vis-a-vis a rotation all the way around. These are the kinds of things that are relevant to propagation, like in these waves for the moments and such and things like that. So in the chapter, he's got the area of the parallelogram. He helps explain and show how rhombuses and other similar quadrilaterals are kind of understood by students. And then, for example, he's got these type A and type B diagrams that, using symmetry or persistence of vision, things that make it possible. It's like, I can see this is totally complicated. These 2 ways which cancel each other out and make it totally simple. Vis-a-vis these other ones, it's possible to see them and say, I can see that there's sufficient detail afforded here that even though there's a symmetry, it's as besides the particulars of the shape that make it so. It's character, analytical character. So he's got a great chapter on that, and then he describes the thinking processes and a bunch of research that went into this, and that it's a study where Wertheimer was from Europe originally and kind of left before World War II. It's for the time and place, and then he has already been familiar with the Gestalt of the science, and so that kind of goes back to more of a school of psychology, and it reflects kind of a rejection of Freud, and a lot that goes on into the internalization of things. and it's pretty famous for most people. It represents an idea of good things. And so what he gets into is as I mentioned, he has a story, and then he has a great kind of explanation of how he went back after this, and so he wanted to understand how this person was thinking. And so he said, I was up for nights just trying to figure out what is going on in this thing. And so here there's quite a bit about the area of the parallelogram and all kinds of reasonings that people have about this. As the student who earlier had this book, he's underlined good interrelatedness. And heuristics. And practical alternatives, especially that can be quickly and readily picked up and discarded. Vis-a-vis formula and definite closures in the deductive analysis. For this, I really would have to say that one of my favorite pastimes when I was a kid was getting those, they're called puzzles, logic puzzles, which are like, given these facts, derive the rest of the facts. I really studied those a lot. And such exercise greatly aided the mental facility. So now, if you excuse me, I'm just kind of looking through, because so this is a long chapter about the parallelogram. Many theorists are blind to the problem, to the difference between such cases and cases which are solved sensibly. They have an easy, ready-made way of avoiding the issue. They notice and notice correctly that in the former, help from past experience is precluded, not in the latter, and they conclude, but the conclusion is blind, that the difference in the former responses is explained simply by the working of all previous associations, all basically of the same nature as in rote learning. So rote learning is important, and as for regurgitation and for presentation of fact, and it's for matters of sensible common knowledge. The idea with foundations being just like, with the minimal amount of that, the foundations always provide everything true and logical otherwise about it. The abstract logically stands entirely on its own and makes itself, it's always a detachable model from otherwise the built-in logic of any concrete thing by its logic. So they're not, these are for questions largely of things that are not arbitrary. So this is where that I was talking about the vertical angles. So the next chapter is about the vertical angles. And so this is basically the idea of this, of the interior angles, is that what's congruent to this outer piece of the angle, where when a polygon has its outer angle, which is obtuse, but there's a section of it which is acute, and then the sum of those all the way around is 2 pi, and it's the same for the circle. So that's where it's kind of like, otherwise there's cases for things when you go from the polygon to the infinite-sided polygon, is it the circle? Or otherwise just a smooth, simply closed, connected curve? Well, at least piecewise it is, yeah, because otherwise it would have finitely many straight sides. So looking into this, and it'll just take me a while because I was just kind of lucked out to find this example. The famous story of young Gauss. So Gauss was in kindergarten or first grade, and shown a diagram and said, compute its area. And so via argument symmetry, he's like, I got it. He reduced it to a closed form in a formula, and kind of grasped that. And his teacher was astonished. But he did. So that's generally recognized as the notions of a prodigy. So I don't know any prodigies. I don't think I've ever really met anybody who's really just a prodigy, like absolutely remarkably so, like the people with perfect memory, or people who are natural computers of the longer numbers, or these kinds of things. Vis-a-vis people with great talent, yeah, sure. I mean, everybody's got talent, but the idea that the the prodigy is just it's something remarkable and different. So if Gauss was a very sharp boy, and it's to be commended his experience with these things. And so the author here, Wertheimer, gets into all these kinds of formulas and means and modes and diagrams and the collection of things about all about this algebra and arithmetic, the numbers, the shapes. He talks about figures and compensation, too much or too little, remainder, just needed, getting things just, where just generally means the perfect juxtaposition for the symmetrical. So carrying on, this chapter continues, and imagine it's in the next chapter of this book, but he describes how the thought process takes place. He talks about children playing a game, and one is better than the other, and so it's a competitive game, and it's sad because the one who's on the losing side takes to quit, and so he talks about ways to encourage people to, play for the learning's sake, vis-a-vis playing for the winning's sake. Well, at the same time, excellence is to be awarded by all means, and excellence is to be recognized, and it's not everybody is excellent in a given random draw. So looking through here, and please excuse me, as I had just hoped to find this, and I should have looked for it before I started the camera, that he goes into a lot of different details of, again, forms, geometries, descriptions, a boss, 2 secretaries, and 4 clerks. They put together things which are different and let things appear structurally different, which are not. Experiments with diagrams, experiments without diagrams. Chapter 5. Finding the sum of the angles of the polygon. See here, I could have found this a lot easier, kind of like a phone book, as we talked about before. It's already sorted. That's the whole point. There's random access to the pages, but you can check each one by what letter it is at. Go for it. The table of contents has this as its title. It should be pretty clear and apparent. This is exactly what it is. So let me see if I can read this briefly. During a conversation at lunch about ornaments, the discussion touched on closed geometric figures such as triangles, rectangles, hexagons, and other polygons. At one point, a friend, an artist, remarked, "The sum of the angles of all such figures must, of course, be the same in every case." See, kind of like when we have our open and closed, in a lot of these discussions back in the differential dynamics, as of after Kazarinoff in the means and the inequalities, and then with regards to the definitions of some of the things with Pappus's theorem and stuff like that, and about the Jordan curve or simple closed connected curve, and what's the inside and outside, and that, and why that is so difficult or just underdefined, and as well with regards to some of the discussions here with regards to the fixed and free and projection and perspective and what that means for geometry. That these are things. Here, Wertheimer continues. At one point, a friend, an artist, remarked, "The sum of the angles of all such figures must, of course, be the same in every case." Everyone laughed. See, this is why, as I look back to saying that, and as was my train of thought about it, I was like, oh, this is something that I would, critically, I would strike as saying that's factually incorrect. You're factually incorrect. Either correct that or you're factually incorrect. It's kind of a thing, right? Being that anyone is welcome to be as critical of themselves as they want, and for that matter, anybody is free to be as critical of other people as they want. So, in this logical language, I always try to do the right thing in this kind of sense. Out of pure self-interest, it's not to be as something not humble. It's like, yes, psychologically, I can understand that people would want to simply not lose, for example. So he goes on. Here we go. Everyone laughed. I found myself in a remarkable situation. I said, of course, the sum of the angles is not the same. For the triangle is 180, for the rectangle 360, for the hexagon 720. But I feel the assertion must be right somehow. It touches an essential point. This feeling continues strong in me. Now, here I might say, well, is that appropriate adverb, strong for strongly? On the one hand, it was clear that the sum of the angles was not the same in the various polygons. On the other hand, I had the feeling that I could not let the matter rest. It had to be cleared up. There had to be a way of seeing through it. There was a beautiful point in it, but I did not know how to get at it. It was impossible to understand or even to express just where the problem lay. The compulsion remained. There must be a solution. What on earth is the matter? For the others taking part in the conversation, there was no trouble. The matter was settled when they saw that the assertion was obviously false. In the hours that followed, in which I had other things to do, the problem continued to be active. After several hours, it had developed to this stage. There is, on the one hand, the sum of the angles A in a figure. On the other hand, there is the closed completedness B of the figure. Between A and B, there is only an and, a simple conjunction. There is the one, here is the other. This and relationship between them is somehow blind. What is really behind it all? What is the trouble? The two must have something to do with each other. It was not a feeling of two contradictory propositions. I was directed toward the positive problem, how can I comprehend? So this gets into kind of the nature of the notion of the continuous and discrete, and the finite and the infinite, and the straight or linear, and the curved, and this kind of thing, the curvilinear vis-a-vis the circular, and this kind of thing. So section 2. The following day, while I was engaged in other work, the idea suddenly came to me, vague, indefinite, and uncertain, something like this. Here is a point. And so he draws a diagram of a point with all the rays pointing inward toward it, or outward. Around a point, there is a complete angular space of 360 degrees, one whole angle. So at this point, when I had read this, I was like, this is speaking to me, and it's helped me to figure it out, because my mind had been chewing on this for a while, trying to figure out, it's like, when I said that, I meant that. And it wasn't just a slip of the tongue, it was as of kind of a matter of fact. So it's this interior angle as of about the circle, or part of this distinction and contradistinction of the point in space. So people often learn by errors, but they have to, they kind of have to know. If they're where learning is considered always some kind of productive exercise, it's always a good thing. Vis-a-vis that which overshadows, or what would be called the conditions somebody to whatever way, in terms of beliefs, desires, and motivations, usual models of psychology, and the fulfillment of needs, and such, the lack thereof. Here is a point. Around a point, there is a complete angular space of 360 degrees. So we usually say 2 pi radians. And then here that gets into, what are radians? And so this is almost as for irradians. a new word made of old words with a meaning made from itself. In its context, it fits. Must there not be something similar to this in the case of the closed figure? But this most hazy notion could not be further clarified at the time. 3 days passed. Whatever I did, there was always present the same strong feeling, the feeling of something unfinished, of being directed towards something I could not grasp. I felt repeatedly that I could almost tell where the trouble lay, upon what it depended, and in what direction the solution would develop, but it was all in a colloidal, indefinite state, so that I could not formulate it concretely. Many times it seemed so clear that I need only write it down, but when I attempted it, the ideas could not really be formulated. So you see, he kind of describes that if you can explain something to somebody and they can infer the same kind of content and meaning, it really represents an understanding. And to an extent, even the rote learning is like that. It's like, this is something that you can learn. And you don't need to think about it. You can just remember it. These kinds of things are great. I need only write it down. I found a similar course in development in many truly great intellectual accomplishments. The same feeling of direct attention with the real situation hazy, colloidal. So the colloidal in those days probably would have referred to like silver iodide solutions and such suspensions of what are between, or that are what are colloids. They're admixtures of a sort. So somehow the form the solution will take is in its essentials on the tip of one's tongue, but it cannot be concretely grasped. It is a condition which may often last for months, with many days of depression during which little success is evident, yet one cannot drop the matter. So here this is kind of referred to as an idée fixe. And so in the discussion of the descriptive differential dynamics, that's kind of the idea, is that it's an idea, and it has a truth attached to it, and it's got a perceived truth. That generally, when we describe such things as our logical, concrete things logically, we just only can describe them as perceived, like so. So here's got a perceived truth, and it's so compelling, what compels one to so carry on this way, that he's thinking about it. It is a condition which may often last, during which little success is evident, yet one cannot drop the matter. Section 3. Again, after 2 days, the following question arose. If I have a point, there is a complete angle around it. Now, if I have a straight line, there is also an angular space around it. And so he's just kind of drawn these rays as pointing into it, as of how many lines do you have to point at a given point from a space to a subspace to individuate a point. This is, from my mathematics, what's called the one or two sidedness of points on a line. And points in a line have one side, and points on a line have two. And then in like a plane, it takes 3 or 4 or 5 different rays pointing at a given point. They're 3, 4, 5 sided that identify this. So this really spoke to me and helps me connect some of the things that I've built in my magical land of wonderful ideas, mathematics and physics and such the harder ideas. Now, if I have such a straight line, how must I proceed to obtain a closed figure? Simply by continuing at the straight line? Not at all. I must break the line at some point if it is ever to form a closed figure. This led quickly to the idea, let me look first at the sum of the exterior angles. And what happened? In breaking, the straight angle broke into 2 side angles. Each of them a right angle, and between them arose a delta, an angle of rotation. So this is what's congruent to this interior part. This is kind of like what's flexing into as something that's inverting in and about the center of the circle, the measure of it. It is the deltas, the rotation, that are the important thing. And in the whole figure as it closes, the sum of the deltas must be a complete revolution, an angle of 360 degrees, no matter how many side angles the figure has. Every side has 2 exterior right angles, 1 at each end. There can be as many sides, therefore as many such angles as one wishes, but in every figure The deltas, the angles of rotation, must make a complete revolution. This was an intuition. I was very happy at this moment. I had the feeling, now I see through the matter. What actually happened? I started with the usual notion of the angles in the completion or closure. See, he's then using deduction which usually just closes things and makes for the stroke that is definite. And it's just matter-of-factly, very directly. But here it's like, because it involves these concepts of projection and perspective, it's profound. So this made me very happy when I read this. And it helped me recall these other things that are part of the opus of continuum mechanics. What actually happened? In trying to see how the closure comes about, the total exterior angle of a corner became 2 right angles plus delta. The 2 right angles became peripheral to the issue. The delta was envisaged with the other deltas as forming a complete rotation. With this conception of the angles, there was suddenly an interlocking of the deltas, the significant angles, with the closure of the figure. The and relationship of big A, the sum of the angles, and big B, the closed completeness, had changed into a coherent, comprehensible, lucid togetherness. A and B were no longer just pieces set up alongside one another. They are now parts of an inner togetherness. The sum of the angles in the closed completedness. Closing the figure required the deltas to complete 360 degrees. This process of integration served as a solution. What had just been just an obscure and unsatisfactory sum now assumed well-defined shape. The idea that the sum of the deltas is 360 degrees came into existence not as some assuming proposition, general statement, or belief, but as an intuition. Seeing in a structured view of the figure the interrelatedness between closedness and all the deltas. So then he gets into the ideas of why it takes up to 5 to make a central point, to make a point. So from my perspective is that going from one dimension to a plane can start with like as few as 3 points. And then topologically, it's kind of well understood and known as like when you get into the Banach-Tarski theorem and the doubling space. And also this matters as for continuum mechanics, why this ends up being important for people who really think that continuum mechanics is important for all of what it is, and elementarily and fundamentally. That this greatly amused me because I've been studying this for a long time, and it helped me find a way to talk my way out of having made that factually inaccurate statement, which is untrue, and being able to not just retract it, but to rehabilitate it, to bring it as to where it's something that was actually more true. So this is what I wanted to relay today, and it didn't take too long. I hope just about half of one of these episodes to fix that slip. The rest of this book is pretty good too. It's from the point of a thinker, and it's really made for people who are just kind of people who would end up having to be responsible for the education of other people, and that they would become successful, and this kind of thing. This can help a lot. Sometimes everything helps. Sometimes nothing does, and the goal is the least that is enough. The sleeve says, an eminent selection on books for education for tomorrow. Adelot Bergson, Blanchard, Bremmel, Caswell, Ducasse. I've heard of Ducasse. Fine, Green, Arbison, Avigers, Henderson, McConnell, Handel, Michaeljohn, Molman, Coos, Mahoney, Murphy, Warner, Loeb, Melby, Sexton, and Max Otto. Right for the booklet, What is Happening in American Education? And then on the back cover it says, another distinguished Harper book, Philosophy in American Education. This book embodies the report to the American Philosophical Association of its commission of 5 members on the function of philosophy in American education. That's not this book. That's a different book. $3 in 1945 U.S. dollars. I have some, but I got this one for a great deal. This book is by Bernard d'Espagne, and what it's called is On Physics and Philosophy. So this is from about 2000, and so if we would relate this to the previous look at, you can't really say it's a study if you haven't even read it, of Badiou, that this is what I'm kind of reading this book, and I'm up to about page 88, and the chapter is Objectivity and Empirical Reality. And so what it is because there's a J.S. Bell is an Irishman, and he came up with some ideas about why special relativity is hosed, or that it's local, and then with regards to the non-locality and all these things that go into it. So this is a cause of a great kerfuffle in physics today, because most people did not have this as their instruction, and in fact some of the things that so relate to it is the problem are counterintuitive, and so it ends up being very problematic when it's kind of difficult to figure out how to explain these kinds of concepts, when it's difficult to even articulate them, and it's difficult to establish the entire dialectic and the whole open and closedness of things, when everything has been built up from its classical linear justification, which is great, which is fine, which is perfect in its own sense. Just not for all of physics, not for like a theory overall, which requires really this whole idea of a theory overall. And necessarily concepts like dual monism for a consistent, complete, and concrete, constant, consistent, complete, and concrete theory, which we can ascertain or attain to. So d'Espagne is studying this entire milieu, and he's kind of, if Einstein is a grandiose hedge, then d'Espagne is also a sort of hedge, meaning whatever he'll say, he'll kind of back it up. But whereas Einstein is like, I'm going to put things out kind of in a way that I won't ever have to take anything back. Like no matter where you're looking at from the picture, it's the same. It's good. Einstein is a grandiose hedge. Well, d'Espagne is a bit more of a micro hedge. And what I mean by that is that every single paragraph he starts is kind of like, we know everything, and so we've defined all these different philosophical aspects that make it so relevant, and the way we're going to look at this from all these different ways, and what holds and what doesn't, and what's the takeaway and what's the give, and this and that. And then in the middle of the paragraph, he'll point to like, and so this is saying this and this is saying that, and they don't agree, and we got to bring them back together, and how's it going to be, and so on and so on, so on and so forth. And the end of the paragraph, he says, forget all that. Now we're just going right back to our dogma, and it's going to be fine. So he's sort of more of a micro hedge, with the idea maybe that he could always point to something and say, see, this is just what I was talking about here. All right, whatever kind of else comes out of it, is kind of a hedge. The hedge is that it's kind of like a lean-to. Whatever you have something leaning, you always have something leaning the other way. It's the hedge. Usually the idea being, hedge via diversity, vis-a-vis that a monoculture has at once the benefits of homogeneity, but the risks of weakness, of single point of failure. So anyways, I pretty much just disagree with this guy, because he doesn't have a very strong opinion. I demand a kind of conscientious sort of opinion that's consistent and what in or out, Remark on the role of the pilot wave. So the pilot wave is one of these notions of Bohm-Broglie that's super classical, the pilot wave, and it's just a super classical model. It's great. free information was a really key concept from this last talk. It's like, well, what's the cap and the limit on the speed of the propagation of information? It's light speed. In a universe where that's also the maximum speed. Well, what if it's infinite? It's like, yeah, what if it's infinite? If metered, the infinite in reality is not absurd at all. It's the laws of large numbers, is what it is. Anyways, back to Despagnet. Let's see what he has to say. Remark on the role of the pilot wave. It is, if not non-separability proper, at least the fact that the wave function is spatially extended explains why the Broglie-Bohm model is compatible with the outcome of the Young fringe experiment. Of course, in this model, any corpuscle passes through but one slit, but it is acted on by the pilot wave, which does pass through both slits at the same time, and which beyond the diaphragm is therefore not the same according to whether this other slit is shut or open. The state of affairs at a place that on the atomic scale is far from the corpuscle trajectory, thus has on the behavior of the latter an influence that may be termed non-local, though no entanglement is involved. Well, this is just kind of the idea that when the particle, when it hits the detector, is detected, that was a wave, and it's so high frequency that where it landed is the particle notion is a conceit. Particles don't really exist. They're just a place where we can make a mark in our observer and our apparatus that's feasible, that's fungible, that in our model we can model the entire thing as continuous instead. And in fact, because and it's must sein. So figuring out the concept of that is pretty tough, because it requires everybody to augment the entire other notions of the phenomenology in the classical, and like it's kind of like ancient Greek geometry or Euclid's. You only get a compass and edge. There are no other tools. So some constructions are going to take you forever. Well, here it's like if you add an Archimedean spiral, then you can trisect angles and square circles and such. If you have one of these tools, geometry, called Archimedean spiral, the idea is to figure out the least amount of that, which then gets related to a mental sense called the object sense. So it can be part of our phenomenology, that it's just the act of a marker measure, or it's just the act of experiencing continuous time at all. It's continuum mechanics. So here we go. The state of affairs at a place that on the atomic scale is far from the corpuscle trajectory, thus has on the behavior of the latter an influence that may be termed non-local, although no entanglement is involved. Well, it's just a wave. Superclassical pilot wave, sometimes ghost wave, pilot wave. Note that in this model, it would just be absurd to take the presence at some time t of a corpuscle within one particular slit as a pretext for attributing to it a wave function that at t would be non-zero only within that slit, and to ground predictions on it. In the model, predictions exclusively depend on the pilot wave as defined by the overall experimental conditions, source, diaphragm, slits, and so on. More generally, while in the model a corpuscle has at all times definite properties, its future depends not in any way on the latter, but merely on the overall wave function. This is what explains why some conceptual difficulties specific to the standard form of quantum mechanics, with which we shall get acquainted later, are not present in the considered model. So it kind of works on his hedge. And this helps explain that the configuration energy experiment is what varies. Kind of like Achilles and the tortoise in a straight or round track. So they have particle physics and experimental particle physics. And so they got like the idea of the collider or the accelerator. So what they do is they take particles, very, very small particles, and accelerate them to up to hard by light speed. Accelerate them fast as they can possibly figure out how to do it. And so some of these are contained in kind of like a circuit, a round accelerator. Ring cyclotron is kind of what you call it. It's a cyclotron, it's a ring cyclotron. And I have a couple books that help display and show the apparatus of those and how to build them from like a tabletop model to what are the usual components that go into making these kinds of things. So it's round. And then it's something like the linear accelerator is basically just point to point. It's like we are making no effort at all to try to keep things on the track. It just goes straight as fast as possible. Well, they're different. And so that's just kind of help explain that in relativity, the theory of relativity, they're considered the same with regards to mass-energy equivalency. But instead they can be considered different because the rotational makes the usual notions of space contraction, mass-energy equivalency, whereas the linear moves the carriage along with it and is Galilean then in a sense in the linear that it can so proceed. So this makes it so that when we look at the sky survey, it's like, we looked at the sky survey and those two neutron stars are shooting at a superluminal jet. So we have to call that an optical illusion or explain science again. It's like, it's got an explanation. You just need to refine your notion of Einstein's relativity and make it more Fitzgeraldian, and then also have it so that it's linear and rotational are separate, kinetics and kinematics. Make up some new Newton's zeroth laws, and everything's just fine. Everything's great. Keeping things simple. Simple and possible to put on so few words is kind of how I feel about these things. Objectivity and empirical reality. Let's, for a moment, read from Despinat. Strong objectivity and weak objectivity, alias intersubjectivity. So, what one of the primary desiderata or requirements of Despinat is this separability, and it's like can our mind pick it up and put it down, and then it's phenomenal while it's set aside. Vis-a-vis that there's no real there's no interaction necessarily between the theory and the experiment at all. Our original program is well on the way. The need to go beyond the familiar concept framework was demonstrated in Chapter 2, and the necessity of going over from multitudinalism to a more holistic view of whatever is meant by reality was established in Chapter 3. What remains to be considered and will hold our attention for a longer time is the philosophically even trickier question, whether or not the objectivist language is of universal use in physics. In other words, it is the question whether or not physical realism may be kept, at least as a universal, everything takes place as if. Of course, these three subjects come within the scope of general epistemology. One might aver that it's overall unfalsifiable the other way, so as far as science is concerned, that's a go. As regards the first two, it is nevertheless on the basis of facts, not exclusively of ideas, that we examine them. Abiding by this method, we shall do the same with respect to this one. 4.1.1. Quantum interference and weak objectivity. So strong and weak are kind of one of these other notions of, like in the theory, sometimes the stronger theory or the weaker theory is the weaker theory or the stronger theory in terms of either what it does or doesn't entail. When Despinat writes weak in quotes here, it kind of can mean it's weak in terms of some of what it is its usual fundamental, like guarantees of inductive a course are let out that is weaker than those strong laws that has a different law that ends up being that the weak version, just like weak convergence or strong and weak in mathematics, is just to relay that the term means within the framework of the things. In the quantum domain, the most significant fact is by far the existence of interference effects involving particles. Well, I mean here, it's just overall a wave model, and then particles are just the central moments, these waves, and the singularities, the origins of these things. That the particles just kind of represent this coalescing when, according to the detector, that things become discrete across the junction the interface, the boundary in the unified model of all of physics fits in this model. As far as I can tell, my entire idea here for foundations is to make just one simple theory at all. The most usual experiment in the quantum mechanics, because you can find it on a tabletop, and also it's easy to have it in a classroom, is the dual slit experiment. And what it is it shows that you can put like a stroboscopic or an emitter of electrons, like pulses briefly, as the wave train and what's called the wave packet, and then it's got two gates that can go through, or slits. And so if it goes through the left or the right, then what happens is that it just kind of waves and points to a line. But if it goes through both, it draws a wave. And so then and also has a constructive and destructive interference pattern as on it. So it's one of the most usual things. It shows, like, just by changing the configuration of the experiment, immediately, as far as it's concerned, that what is the surrounds of it affects not just the thing that is together and holistic, how that is so. Consider a diaphragm with two parallel slits. If a particle beam passes through this device and impinges on a screen, so-called interference fringes appear on the latter, which cannot be explained if the particles behaved according to classical physics, and hence seem to reveal that they somehow possess wave-like features. Because of its similarity with Young's original experiment bearing on light, this phenomenon is often called the Young slit experiment, even when it involves particles other than photons, and we shall take up this convention. Note that for the fringes to appear, it is necessary that, on their way, the particles should undergo no appreciable interactions. If, for example, some dense gas were blown between the diaphragm and the screen, with the consequences that very many particles would hit molecules of that gas, the fringes would fade. At high density, that is, if such interactions become the rule, it is expected that the observed behavior of the particle would simulate the one they would have if they obeyed classical physics. Their impacts on the screen would gather within two blobs corresponding to each one of the two pencils of light if the particles were photons issuing from the two slits. The formation of such interference phenomena is a massive, bulky fact, the conceptual bearings of which are all the more considerable as it is but one out of many equally uncommon facts, all of which are well accounted for by an extremely general mathematical formalism called quantum mechanics. That's a little grand, and it's not much of a hedge. So yeah, Despaigne would have at the same time, well, it's accurate. It'd have a hard time, trying to walk that back. However, the words accounted for should, as we already know, be understood here in a well-specified and somewhat restrictive sense. Yes. Quantum mechanics synthesizes these facts, encompasses them in its equations, and yields rules for predicting them. It has to, because it can never be wrong. Quantum mechanics is never wrong. But the light it sheds on them does not reach beyond that point. If we are anxious to better understand what takes place, it is up to us, along with many other interested people, to try to find out the answer. Then he gets into a discussion of the fragments, kind of as we were talking about. And this thing. So I'm not going to spend too much more time on Despaigne in this talk here, but he gets into the Born rule, that the numbers are conserved. There's no half numbers or whatever, and it's like, well, then we just have particle statistics according to their half numbers. And the time-dependent wave function, here we can refer to the discussion of Swanson and the path integral about the time ordering and the analysis that makes the line integral. Velocity, field, force, and so on. So this is a pretty great book in terms of, like, the language then is very is very academic, meaning he spent years and years just writing on his desk, filling in this book until he was entirely happy that he had put in so much verbiage to get everything set up that he could point to any particular discussion later and say, aha, I see you're relating things in this frame, in this mood. So it's not a lot different than like a deconstructivist account of a text, which is basically anybody's own text, and anybody has their own theory, and it's perfectly true for them, or insofar as it isn't, it's personal, that this is the sort of academic work which is very familiar with the surrounds. It's so in terms of its requirements and desiderata, being this micro hedge, he can always just reject anything for pretty much any reason, and vis-a-vis claim all these different desiderata and requirements from what it must have set. That my goal would then be to establish from these very particulars of what's the realist and objectivist and the operationalist and instrumentalist, what would be these fewest things for the number sense and word sense and object sense to arrive at this paleo-classical modern continuum mechanics theory, and the rest would follow. Well, that's our talk for today, pretty much. I hope this day is great for you, and things go well. And I shall so hope that this was enlightening in usual sense. And then with regards to the whole idea of the difference between points on a line as of our continuous field, it's like I see you divided 2 by 3. It's 2/3. It's a point on a line. Vis-a-vis points in a line, I see you're going from 0 to 1 in a line. Contiguous points. That's kind of where that starts, and it's related basically to, in physics, what's called superstring theory. They got open and closed strings. And then together they make a chain or they make a net, kind of whether it's smooth or whether it's rough, as with relation to these earlier talks that have gone on largely here verbally. And then in the hundreds of thousands of pages, I wrote on to Usenet and all this kind of stuff, which is quite factually correct, thoroughly, and that I adhere to. Well, all right, so long. Moment in motion. Geometry is motion.